Hello friends, welcome to Electrical Machines class lesson 9. In this lesson we will learn parts of a DC machine and their functions. The parts are broadly divided into two, that is the stator and the rotor. Before we look at the parts and their functions, let's start with a definition. What is a DC machine? It is an electromechanical device that converts direct current, DC, electrical energy into mechanical energy, or vice versa. It can function as either a DC motor or a DC generator. Both types of DC machines share a similar construction. The main parts are 1. Stator. This is the stationary part. 2. Rotor. This is the rotating part. 1. The stator houses yoke or frame, field poles, field windings or exciting coils, interpoles or commutating poles. 2. The rotor houses armature core, armature winding, commutator, brushes, shaft. 3. The other parts of a DC machine are bearings, cooling fan, end shields. The below is a diagram of a DC machine. As shown, we can see the yoke, field windings, armature core, armature winding, commutator and field poles. Now let's look at the first part, that is the yoke. It is also known as the frame. It is usually made of cast steel or cast iron. Functions of the yoke. 1. It provides mechanical support and protection for internal components of the machine. 2. It provides a low reluctance path for the magnetic flux to complete its circuit. 3. It is used for mounting the machine, often with feet for flat installation or flanges on the end covers for vertical mounting. Now let's look at field poles. They are the stationary magnetic poles fixed to the inner surface of the yoke in a DC machine. It is usually made of cast steel or laminated soft iron for high magnetic permeability. Each field pole has two main parts. 1. Pole core, made of laminated soft iron to reduce eddy current losses. Provides a path for magnetic flux. 2. Pole shoe, wider part of the pole, attached to the pole core. Helps spread the magnetic flux evenly over the armature surface. Provides mechanical support for the field winding. Function of field poles. 1. Produce the main magnetic field. The field poles generate the stationary magnetic field when current flows through the field windings. 2. Guide magnetic flux. They direct the magnetic flux through the air gap and armature core, which is essential for voltage generation or torque production. 3. Ensure uniform flux distribution. The pole shoes help distribute the magnetic flux evenly, minimizing sparking and improving performance. 4. Support field coils. They hold the field windings firmly in position inside the yoke. Now let us look at field winding. Is a coil of wire wound around a magnetic pole core to create a magnetic field when current flows through it. Is made of enameled copper wire. Wound on laminated pole cores made of soft iron or steel. The coils are connected in such a way that adjacent poles have opposite polarities, north-south north-south. The number of turns and current through the winding determine the strength of the magnetic field. Function. 1. Produce magnetic field. 2. Establish flux for induction. 3. Control output voltage, in generators. 4. Help in speed control, in motors. Types. 1. Shunt field winding. Has many turns of fine wire and has high resistance. Used in shunt generators and motors. 2. Series field winding. Has few turns of thick wire and has low resistance. Used in series generators and motors. 3. Compound field winding. Is a combination of both shunt and series windings. Used in compound machines for better voltage and speed regulation. Field winding is the magnetic heart of the DC machine. Now let us look at interpoles. Are small, narrow poles placed between the main field poles in a DC machine. They are also known as commutating poles. They are fixed midway between the main poles. Each interpole has its own winding, wound around a small iron core bolted to the yoke. The polarity of each is the same as the next main pole in the direction of rotation. Function of interpoles. 1. Improve commutation. Interpoles produce a magnetic field that neutralizes the reactance voltage caused by the armature's self-induction during commutation. This helps in spark-less commutation at the brushes. 2. Reduce armature reaction effects. The flux produced by the armature distorts the main field. Interpoles counteract this distortion, maintaining proper magnetic conditions under all loads. 3. Automatic compensation. Since interpoles are connected in series with the armature, their flux automatically increases or decreases with load current, providing self-adjusting compensation. 4. Maintain machine efficiency. By ensuring smooth current reversal and preventing sparking, They reduce brush wear and enhance efficiency and reliability of the machine. The next part is the armature core. Is the rotating part of a DC machine, both generator and motor, that carries the armature winding. It is made of soft laminated iron sheets, usually 0.4 to 0.5 mm thick. The laminations are stacked together and mounted on a shaft. The slots on the outer surface of the core hold the armature winding. The laminations are insulated from each other by a thin varnish layer to minimize eddy current losses. Functions: 1. Carries magnetic flux. 2. Houses armature conductors. 3. Supports rotation. 4. Reduces losses. The armature core is the magnetic and mechanical heart of a DC machine. The next part is the armature winding. It is the set of conductors placed in the slots of the armature core. It is the electrical winding where the electromotive force, EMF, is induced, in a generator, or through which current flows to produce torque, in a motor. It is made of copper conductors. Conductors are placed in armature slots and insulated from the core by mica or varnish insulation. The ends of the conductors are connected to the commutator segments, which convert AC-induced EMF into DC output. Function of armature winding: 1. Converts energy. It transforms electrical power into mechanical power, as torque, in a motor, or converts mechanical power into electrical power in a generator. 2. Induces EMF. The relative motion between the armature conductors and the magnetic field induces an electromotive force, EMF, in the winding, which opposes the armature current in a motor and is the source of the output voltage in a generator. 3. Carries current. It is the main circuit that carries the current, known as armature current, required for the motor's operation. 4. Generates torque. It produces electromagnetic torque by conducting current through a magnetic field, causing the rotor to spin. Types of armature windings. There are two main types depending on how the conductors are connected. 1. Lap winding. Each coil is connected to the next coil under the same pole. The number of parallel paths, A, equals number of poles, P. Used for low voltage, high current machines. Example: DC generators for welding or electroplating. 2. Wave winding. The coil ends are connected to commutator segments 2 poles apart. The number of parallel paths, A, equals 2, regardless of poles. Used for high voltage, low current machines. Example: DC generators for lighting or power supply. The armature winding is the electrical heart of a DC machine. This is because it's where electrical and mechanical energy are converted to each other. The next part that we will look at is the commutator. A commutator is a cylindrical assembly made up of copper segments, each insulated from the next by a thin layer of mica. Is a rotary switch found in DC motors and generators that reverses the direction of the electric current to the armature. Functions of the commutator. In a DC generator, the commutator converts the alternating current, AC, induced in the armature output terminals conductors into direct current, DC, at the output terminals. It acts as a mechanical rectifier. 2. In a DC motor, it reverses the direction of current in the armature conductors every half rotation. This ensures that the torque produced always acts in the same direction, allowing continuous rotation. The next part is the brush. A brush is a block of carbon or graphite that presses against the commutator segments to conduct current between the rotating armature and the external circuit. Functions of brushes. 1. In a DC generator, it collects current from the commutator, which carries current from the armature winding. They deliver this current to the external load circuit. 2. In a DC motor, it supplies current from the external DC source to the armature winding through the commutator. This enables current to flow in the armature conductors and produce torque. It is made of carbon or graphite, sometimes with copper added for better conductivity. It is held in brush holders with springs that press them lightly against the commutator. Shape: usually rectangular blocks. The below is a diagram of the brush. As is shown, it has a brush holder and the spring. The next part is the shaft. A shaft is a solid cylindrical rod, usually made of high-strength steel, mounted on bearings so it can rotate smoothly inside the machine. Functions of the shaft. 1. Supports the armature. It carries the armature core, commutator, and fan, keeping them aligned and balanced. 2. Transmits mechanical power. In a DC generator, it transfers mechanical energy from a prime mover to the armature where it is converted to electrical energy. In a DC motor, it transfers mechanical power, torque, from the armature to the external load. 3. Provides mechanical connection. It connects to couplings, pulleys, or gears for power transmission. The next part is the bearings. A bearing is a device that supports and guides a rotating shaft, enabling it to rotate freely while keeping it correctly aligned within the machine. They are mechanical components that support the rotating shaft, allowing it to spin smoothly with minimal friction. They are essential for ensuring stable, efficient, and quiet operation of the machine. Functions of bearings. 1. Support the shaft. Bearings hold the shaft in position and carry its weight, preventing it from sagging or moving out of alignment. 2. Reduce friction. They minimize friction between the rotating shaft and stationary parts of the machine, ensuring smooth motion. 3. Maintain alignment. Bearings keep the armature and commutator properly aligned with the field poles, which is crucial for efficient electrical operation. 4. Enhance durability. By reducing wear and vibration, bearings increase the lifespan of the machine. 5. Allow rotation with stability. They ensure the shaft rotates freely and steadily, maintaining balance during operation. Types of bearings in DC machines. 1. Ball bearings. Commonly used for small and medium-sized machines. Provide low friction and high-speed capability. 2. Roller bearings. Used in larger machines where heavier loads are involved. 3. Sleeve or bush bearings. Simple design, often used in low-speed or light-duty applications. It is made of hardened steel, bronze, or anti-friction alloys. The other part is the cooling fans. A cooling fan is a set of blades or vanes mounted on the shaft of a DC machine that rotates with the armature to circulate air inside and around the machine for cooling purposes. Functions of a cooling fan. 1. Dissipate heat. It blows air over the armature, field windings, and other internal parts to carry away the heat generated by electrical and mechanical losses. 2. Maintain safe operating temperature. Prevents overheating of insulation, commutator, and bearings, thereby increasing the machine's lifespan. 3. Ensure continuous operation. Keeps the machine running efficiently and safely during long periods of operation. 4. Improve efficiency. By maintaining an optimal temperature, it reduces resistive losses and prevents performance deterioration. Now let us look at the end shield. It is also called an end bracket or end cover. It is a metallic cover mounted on each end of the DC machine to support the bearings and enclose the internal parts such as the armature and shaft. Usually made of cast iron or aluminum alloy for strength and durability. Functions of an end shield. 1. Supports bearings. It holds the bearings that support the rotating shaft of the armature, ensuring smooth and aligned rotation. 2. Provides mechanical protection. It encloses and protects internal components like the armature and commutator from dust, dirt, and mechanical damage. 3. Maintains alignment. It helps keep the shaft, armature, and bearings properly aligned, which reduces vibration and wear. 4. Facilitates cooling. Some end shields have ventilation holes to allow air circulation for cooling the machine. 5. Ease of maintenance. They are removable, allowing technicians to inspect or replace internal parts like brushes, bearings, and the commutator. Thank you for watching our channel. Please like, comment, share, and don't forget to subscribe. May God bless you.